Okay, we will continue a little more reviewing the last week's subjects. And this slide was where we left off, the control styles of software systems in architectural design. There are two ways of flowing control and data among subsystems. I'm sorry. One way is centralized control, and the other is event-based control. In the centralized control, we have two alternatives to manage the execution of other, to manage the control flow. First, a control subsystem takes responsibility for coordination of the control flow among other subsystems. And these two alternatives in centralized control are the control return model and the manager model. In the control return model, the control flow is managed, is organized through our familiar top-down subroutine model. Here, control starts at the root of a subroutine tree, and through subroutine calls, the control moves downwards to other subroutines. And you can see it here in this diagram. The control starts here, and through subroutine calls, the control may move to other routines in the direction downwards to the tree. Okay, this is obviously applicable to sequential systems, and the manager model or managerial model is usually applicable to concurrent subsystems. Here, one system component coordinates other system processes, and its diagram is given here. A system controller coordinates the flow of control among other subsystems, and using this way of control flow, concurrent subsystems may be processed concurrently. Well, the second alternative, how the control flow is coordinated, is event-driven systems. In event-driven systems, the control of the subsystems processing the event is driven by externally generated events. And there are two primary event-driven models here, broadcast models or interrupt-driven models. Here, before talking about the different event-driven models, I need to say that an event here is doesn't need to be a binary signal only. Even an input command or some signal within a range of values can also be called or named an event. And by external generated events, we mean events whose timing is not within the control of the software system we are talking about. It is the events are usually the events usually have timings which is beyond the control of the software system we are talking about. Okay, the alternatives in the event-driven models, broadcast models, and interrupt-driven models. Here in broadcast models, an event is broadcast to all subsystems. Any subsystem which can handle the event can do this. This is effective in integrate. Okay, I'm sorry. And interrupt-driven models are control flow models for the real-time systems, where interrupts are detected by an interrupt handler and passed to some other component for processing. Here, I need to add that broadcast models are usually models that coordinate the control uh, for software systems where timing requirements are not tight, where there are not strict timing requirements. But interrupt-driven, I'm sorry, real-time systems are systems where there are strict or tight time requirements. So for these type of systems, broadcast models are too too loose systems. Timing control is not done in broadcast system models. So that's why real-time systems can only use interrupt-driven models as their control flow models. Okay, let's discuss in a little more detail the broadcast models. They're effective in integrating subsystems on different computers in a network. Well, here, for example, you can see a broadcasting system, selective broadcasting system. Here, event message handler carry all events that are available, and the subsystems can connect to these events through this event message handler. Here, subsystems register an interest in specific events. When these occur, control is transferred to the subsystem, which can handle the event. And these subsystems, the subsystems registers are available in the event message handler. And event message handler, whenever an event comes, and this is in interest of any subsystem, then the event message handler connects the corresponding event with the interested subsystem. Each type is associated with a memory location, and the hardware switch causes its transfer to its handler. So I'm sorry. Control policy is not embedded in the event and message handler. Subsystems decide on events of interest to them. That's why some conflicts may occur if more than one subsystem shows interest to the same event. Well, here, subsystems don't know if or when an event will be handled. So that's why all this registration of subsystems into the events they are interested in. And that's why they have to wait for this event to occur. And that's why they lose time. And that's why this model is not suitable for real-time systems, because real-time systems have strict timing requirements, and this way they cannot fulfill these time requirements. Okay, so that's that makes interrupt-driven systems make it possible for the real-time systems to fulfill their requirements, because there are known interrupt types with a handler defined for each type. So this way, the real-time systems don't have to wait in case an interrupt if they are interested in an event, then they right away make the request through the interrupt, and the interrupt fault handler does the necessary or takes the necessary action for that. Here, each type of interrupt is associated with a memory location, and the hardware switch causes transfer to its handler. This allows fast response, but complex to program and difficult to validate. So interrupt-driven disadvantages, they're difficult to validate and they're complex to program. But the advantage is that they allow fast response. Here, when an interrupt request comes to the interrupt vector stimulates the necessary handler. It warns the necessary handler, and the handler starts executing the correct process to handle the relevant fault. Okay, that was the review of the last week's lecture. I still wanna get the questions. If you have any, you can write it through the chat panel, and I can answer the questions. Or otherwise, I will jump to the next chapter, the distributed software systems. Okay, any questions? Okay, then I will pass to the distributed software systems. Okay, can everyone see my screen share? Can you see the chapter 6 file? Okay, Ali gave an answer. I think all others can see that too, I assume. So I start with the chapter 6 then. Well, distributed systems have been important after the second half um, of the 1980s with the emerging of the idea of computer networking. And today, virtually all computer-based systems, all large computer-based systems are distributed systems. Here, information processing is distributed over several computers rather than limited into a single machine. And that's why distributed software engineering is extremely important for both enterprise computing systems and for critical systems too. Okay, in distributed systems, there are 5 system properties that are important characteristics that identify the distributed systems or distributed approach to systems development. For example, resource sharing is one of them. Here, a distributed system allows the sharing of hardware and software resources, such as disks, printers, files, and compilers. And another one is openness. Here, this is an important characteristic because we may use equipment and software from different vendors, and may they have to go along. They have to be able to communicate with each other. Another characteristic of distributed systems is concurrency. Concurrency is important. Distributed systems are normally open systems. I'm sorry, in a distributed system, several processes may operate at the same time on separate computers on the network, and these processes may communicate with each other during their normal operation. Scalability, on the other hand, is important because at different time points of the system run, there may be different levels of demand to the system. In these cases, it is extremely important that the software system can serve without any compromise to its quality. So that's why scalability ensures that with the increased throughput by adding new resources in these at these time points where more demand is delegated into the software system is guaranteed. Another system characteristic is fault tolerance. Fault tolerance is the ability of the distributed systems to continue in operation after a fault has occurred, especially since the distributed systems are communicated using a network in the middle. Some problems may occur with some nodes of the system, and it is important that these failures, these node failures, doesn't affect the performance, the overall performance of the distributed system. So that's why fault tolerance is another distributed system characteristic that needs to be taken into consideration. Okay. Well, distributed systems, that the system is distributed, has its own advantages too. One of them is complexity. Typically, distributed systems are more complex than centralized systems. Why is that? Because that the system is distributed, it makes it more difficult to understand their emergent properties and to test these systems. For example, rather than the performance of the system being dependent on the execution speed of one processor, it depends on the network bandwidth and the speed of the processors on the network. So that makes it complex to understand how their emergent properties are going to be defined. Security is another disadvantage, and that's because since there are many nodes of the distributed system, and these communicate through a middleware or a network in between them, now the system is more vulnerable to external attacks. So to come up with a more secure system, distributed system, is now much harder. Manageability is another problem, another disadvantage. And here the computers, okay, we are now talking about a multiplicity of computers. There may be different types of computers, they may run on different types of operating systems, and to manage this system with heterogeneous nodes becomes more manageable, more difficult to manage. So more effort is required to manage such systems. And unpredictability is another problem for distributed system advantages, because now we have a network, and not only does the processor load and a factor about how the responses of the system will be, but the network load is going to play an extremely important role in determining the responses of the system. So unpredictable responses may occur due to the network load, which is beyond the control, most of the time beyond the control of the software system itself. So that's why unpredictability is another distributed system disadvantage. Okay, well, architectural types of distributed systems can be grouped into two: client-server architectures and distributed object architectures. In client-server architectures, the services are distributed, and they're provided by servers and requested. Actually, the roles are distributed. The distributed services are provided by servers and requested and used by clients. So one group of processes are client processes. These processes use the services, and another group of these processes are servers that provide these services. In distributed object architectures, on the other hand, there are no distinction between clients and servers, because each each distributed object can both play the role of a server and or a client. For all distributed systems, there is another component, and this is called middleware. This middleware is used to have all computers of the distributed system, all rather processes of the distributed system communicate with each other. Software that manages and supports the different components of a distributed system, in a sense, it sits in the middle of the system. That's why it is called the middleware. Middleware is usually off the shelf rather than specially written software. Here, off the shelf means that it is readily available and can be purchased, can be taken from the shelf, and it is ready to use. Mostly, a middleware is named off the shelf because it is readily available, can be taken from the shelf, purchased, that means can be purchased and is ready to use. Okay, for the well, just a little a reminder for you. If the meeting is interrupted at the end of 40 minutes, well, it says that we have 9 minutes and 38 seconds left, then we will connect again. I will send you an invitation again. Okay, examples to middlewares are transaction processing monitors, data converters, and communication controllers. Okay, one type before going into client server or distributed object architectures, let's see the multiprocessor architectures. This is the simplest distributed system model. Here, the system is composed of multiple processes which may but need not execute on different processors. So more than one process may run on the same processor. But since we're talking about a distributed system, this type of systems mean a multiplicity or a multiple number of processors on which multiple processes run. Architectural model of many large real-time systems. Multiprocessor architectures are the architectural model of many large real-time systems. Here, there is a process-to-processor distribution, which is either pre-ordered or under the control of a dispatching system, dispatching hardware, let's say. Okay. Here you can see a typical multiprocessor system. This is a traffic control system. As you see here, there are a number of traffic flow sensors and cameras. These transmit information to the sensor control process. Sensor control process pre-processes and processes that, these signals, and then transmits them further to the display process, so that the operator consoles can show to the corresponding people this information. And it is further transmitted to light control processes where this information is processed, and the necessary information such as how long the red light and green light should be on is computed, and it is this way the lights make their task, perform their task. So these are the input units to the distributed control system, and these are the output unit. And these are the processes that run possibly on different processors, but they don't need to run on different processors. They may also run at the same processor. Okay, now this brings us to the client-server architectures, the second architectural type for the distributed systems. Here, we mentioned that the roles of the clients and servers are separated into different processes. The application is modeled as a set of services that are provided by servers and a set of clients that use these services. Client knows of servers, but servers need not know of clients. Since clients are the requester for services, they know servers, but servers are only providing services, so they don't need to know of clients. Clients and servers are, of course, logical processes. The mapping of processors to processes is not necessarily one-to-one. So, in other words, in this diagram, you see a possible distribution of server processes between server processes and client processes. As you see, here there are 4 server processes, and each of them has a number of clients that they provide services to. For example, S1 provides services to 5 client processes, and S4 provides services to 2 client processes, and etc. Okay, and this here is the processor to process distribution. You can see here that we have 2 server computers, for example, and these server computers, on these server computers, we run 4 server processes. Okay, on this computer, on SC1, on the first server computer, S3 and S4 server processes run, and on the second server computer, we run the two first S1 and S2 server processes. And as you can see, there is again 6 client computers, and on these 6 client computers, we are running 12 client processes, and they are not uniformly distributed. For example, computer 1 and computer 2 run client process 1 and client process 2. Computer 3 runs client process 3 and 4, and etc. etc. Okay, so this diagram shows a typical distribution of client and server processes into client and server computers. Okay, well, another let's say a more developed version of client-server architectures is the layered application architecture. Well, here we logically separate the components of the software into 3 groups. Well, for example, the user interface portion we run in the presentation layer. Here, this layer presents the results of a computation to users and collects user inputs. The application logic is located in the application processing layer. This layer provides application-specific functionality. For example, in a banking system, banking functions such as open account, close account, etc., are located in the application processing layer. And finally, in the data management layer, the data management layer is responsible for database operations. It handles or it manages the data operations. So at least these 3 logical separation of the different components of the software gives us an idea about how we can encapsulate different portions of a software product. Now, this is the diagram of whatever what I explained you, or what we discussed in the previous slide. As you see, presentation layer and application layer, application processing layer, are in bidirectional communication, as well as the application processing layer and the data management layer. But the presentation layer doesn't have any communication with it, doesn't have any direct communication with the data management layer. And we also know, or we also make sure that no user interface code is included in the application process.